Hey geometry students, it's Mrs. Fellon back again. We are on the last video for this for this unit. I'm going to put 6.5 and 6.6 together just because they kind of are related obviously together, and I just feel like we can kind of get both of the main points kind of done in one video to save us a little bit of time. All right, I am on page 186 of your student journals. Okay, first and foremost, the first thing I'm just going to kind of talk through. We're not actually going to do a whole lot of this just because you will probably get more information or more practice with this later. It's just going to do an introduction on what an indirect proof is. So it's a proof by contradiction, which is basically, and so there are 3 steps what you have to do. I'm just going to kind of walk through them real quick. Number 1 is identify the statement you want to prove. You are then going to assume temporarily that this statement is false by assuming that the opposite is true. So this is a very odd way of doing a proof. We don't do this a whole lot, which is why we're not going to spend a ton of time on this. Step 2, you're going to reason logically until you reach a contradiction. And so basically what you're going to do is you're going to prove like why that is not true. And then you're going to point out that the desired conclusion must be true because the contradiction proves the temporary assumption is false. So there are some 3 basic steps, like I said, in terms of writing an indirect proof. We are going to write I'll show you an example later on about how to do a proof. We're not going to get into real depth about indirect proofs, however. There are quite a few theorems in these last 2 sections that I did want to talk about. They're fairly straightforward in terms of like, common sense type things. So triangle longer side theorem. So it's really appropriately named. Basically what it states is if one side of a triangle is longer than another side, then the angle opposite the longer side is larger than the angle opposite the shorter side. And so we've talked about this a lot in my classes, I know, that basically there's a relationship between, and this holds true for like all kinds of polygons, but there's a relationship between the length of the side of a triangle in this case and then compared to its angle across from that side. So the longer the side length, the longer the angle, or the larger the angle across from it. The shorter the side length, the shorter the angle across from it. So in this scenario, if you see that A to B is 8 and B to C is 5, then you know that obviously those 8 is bigger than 5. So that means that angle C has to be bigger than angle A. So because angle C is across from the larger line segment. So again, kind of common sense in the sense that we've already kind of talked about that, and we know that like isosceles triangles, if they're equal and so forth, that we know that the angles across from have to be equal. That base angle theorem that we talked about in previous units. Triangle larger angle theorem. If one angle of a triangle is larger than another angle, then the side opposite the larger angle is longer than the side opposite the smaller angle. Again, same basic concept. This time we're starting with 2 angles. So if we know this angle is bigger than this angle, then what that means is the side across from it, so in this case BC, has to be larger than the side across from C, which is A to B. So it holds true, so the bigger the angle, the bigger the side across it, the bigger the segment, the bigger the angle across from it. So again, it kind of holds true both directions. Triangle inequality theorem. So this is the sum of the lengths of any 2 sides of a triangle is greater than the length of the third side. So basically what we know is that in order for a triangle to quote unquote work, in other words, if I gave you 3 line segments, and let's just say I'm going to make one up here. Let's say I gave you 5, 2, and 7. And I said, okay, you're going to draw a line, you're going to draw a triangle that has, side lengths of 5 centimeters, 2 centimeters, and 7 centimeters. The problem with that is I made those numbers up, right? And I gave them to you. In theory, that kind of looks like, okay, it's 3 sides, it should work, right? Well, the problem is that it doesn't. And the reason why is because if you add up any 2 sides of the triangle, so let's say if I add up A to B and B to C, it has those 2 distances, those 2 lengths have to be greater than the third side. So if you notice, A to B is 5, B to C is 2. If you add them together, you get 7. 7 is not greater than 7, and obviously it's equal to, and therefore there's no way for you to connect 5 centimeters, 2 centimeters, 7 centimeters, or even if you change the unit to feet or mile, it doesn't really matter. There's no way to make those 3 segments form a triangle. And so you just have to be careful that when you're looking at 3 measurements, that's a quick way to kind of determine if those measurements do indeed form a triangle. So again, any 2 sides have to be greater than the third side. So in this one, it didn't work because 5 plus 2 here is not greater than 7. All right, we're actually going to skip ahead to page 191. I'm just going to talk through a couple more theorems before we get into some practice problems. You are going to need some paper today because I'm going to go through a few different examples. All right, this one's called the Hinge Theorem. So the Hinge Theorem states, if two sides of one triangle are congruent to two sides of another triangle, and the included angle of the first is larger than the included angle of the second, then the third side of the first is longer than the third side of the second. All right, so let's see if we can, piece this together and make this make sense, right? So here's what we're given. We're given that two sets of sides are congruent, okay? Then we're given that we have two separate angles. Obviously, the angles are not congruent. So one's 88, one's 35. So this is kind of using the theorems that we just talked about. What we know from this then is this side WX has to be greater than side ST because of the fact that the angle is larger than that angle. So again, we're given two sides of a triangle. We are given an included angle. It's not congruent, but we're given an included angle. The bigger the angle, the bigger the side across from it. And that's basically what this goes back to. Converse of the Hinge theorem is exactly the opposite. If two sides of one triangle are congruent to two sides of another, and the third side of the first is longer than the third side of the second, then the included angle of the first is larger than the included angle of the second. So again, a lot of words for basically saying we're given two sets of sides are congruent. We're given a side, that third side. We're given the measurement. The bigger the side, the bigger the angle across from it. So if I gave you this drawing, what I would know is that angle C has to be greater than angle F because of the line segments A to B, which is 12, is greater than D to E. So again, just kind of going back to knowing that the bigger the angle, the bigger the side. That kind of scenario is holding true. All right, so those are all of our theorems, I guess, that I would like us to kind of talk through. As you can see, a lot of them are pretty straightforward and also kind of relate to each other, right? They're all kind of using the same terminology. Grab some paper. I'm going to walk through some examples with you that are not in our student journal. So I'm just going to have you kind of write this down on a separate sheet. You can pause the video if you needed to and copy these down or just follow along as we go through. Some of these are pretty basic. So anyway, let's go ahead and get started. So the first one, I gave you an example of a triangle, as you can see, and it says list the angles of a triangle ABC in order from smallest to largest. So what I gave you here is 3 side lengths of a triangle, and again, I'm using that information about, obviously, the bigger the side, the bigger the angle. So if I want mine from smallest to largest, be careful that you're putting this in the correct order. So the smallest side would have the smallest angle across from it, which means that angle A would have to be, so the measure of angle A is going to be my smallest. So it says list the angles in order. So measure of angle A, or you can just say angle A, I guess. We don't have to talk about the measure. The next one would be the next smallest side, which would be A to B, which is 12. So that would be angle C. And then, of course, our last side, which is the longest side across from it, which would be angle B. So in order from smallest to largest would be angle C, angle A, angle C, angle B. Okay. Again, pretty straightforward, right? Let's do a couple others. Next example, a triangle has one side length 6 and the other of length 15. Describe the possible lengths of the third side. All right, so this one's a little bit more, you have to use a little bit more brain power to kind of figure out this one. But what I like to do is I like to start with a drawing. So just draw a triangle. I didn't tell you what kind of triangle it is, but it doesn't really matter in this case. So a side of a triangle has side length 6, so I'm just going to make this one 6. Another is 15. Describe the possible lengths of the third. So I'm just going to call that third side length X. And so there's a couple things that I want us to make sure that we are remembering here. So going back to that theorem that stated that any two sides of a triangle must be, if you add up any two sides of a triangle, it has to be greater than the third side. So which means that if I add, so if I add X plus 6 together, it has to be greater than 15. So what I'm doing is I'm setting up an inequality, a rather basic inequality, but an inequality. So I'm saying if I add these two sides, it has to be greater than 15. So let's try it. So that means if I solve for X here, I know that X has to be greater than 9. So as long as X is greater than 9, then I know that if I added those two together, it would it would work with that theorem. So it would be greater than 15, and thus I should be able to make a triangle with it. Same thing goes here. I would have to check, these two sides, x plus 15 has to be greater than 6. Well, obviously 15 is already greater than 6, so we don't really need to worry about that. So x can really be any number in the whole wide world as long as, as long as it's positive, it would be greater than 6. So the third thing we have to check is that 6 plus 15, so my next inequality is 6 plus 15, has to be greater than x. So 6 plus 15 is 21, and so that means that if I add these two sides together, it has to be greater than that side. So what I found here by doing this is I found that x must be greater than 9 in order for these two relationships to hold true, right? X plus 6 has to be greater than 15. So in order for that to happen, x has to be greater than 9. I also found that x has to be less than 21 because 6 and 15 have to be greater than whatever x is. So 6 and 15 equal 21, which means x has to be less than 21 in order for this to be a triangle. So I kind of figured out both ends of the spectrum in terms of the possibilities of what x could be. So the final answer would be x has to be less than 21, but greater than 9. So it's my compound inequality here. Those are the possible values for x. All right, let's go on to the next one. In this example, I'm asking you to decide if the side lengths form a triangle. So what I'm getting at here is kind of like the drawing or the example that I gave you on the first page when we first started. I'm giving you 3 random lengths. I'm not putting them into a triangle themselves. I'm just saying, do they form a triangle? So what you're going to do is you're going to double check that all of these things hold true. So if you kind of think of that as like these two side lengths, so 5 and 7 have to be greater than 12. 7 and 12, if I add them together, have to be greater than the third side, which is 5. And then 5 and 12 have to be added together, have to be greater than 7. If all 3 of those statements are true, then we know that those three measurements can indeed form a triangle. The problem is that this one, as you notice, 5 plus 7 is not greater than 12, it's equal to 12. So this one is no, which means that this is not possible. So decide if the side lengths form a triangle. The answer would be no, they don't. Another example, if I give you 4 feet, 9 feet, and 10 feet, again, what you would double check is that, let's say we add 4 and 9 together, it has to be greater than the third side. If I added 9 and 10 together, it has to be greater than the third side. And if I added 4 and 10 together, it has to be greater than the third side. So as long as all 3 of those statements are true, then we know that these 3 measurements can indeed form a triangle. So 9 plus 4 is 13. 13 is greater than 10, so that checks out. 9 plus 10 is 19, which is obviously greater than 4. And 10 plus 4 is 14, which is greater than 9. So the answer is yes, those 3 measurements do indeed form a triangle. All right. Now let's kind of move on to 6.6, so some more examples from that section. This is a little bit more kind of getting into more of the proof stuff, but again, using the same relationships that we just kind of talked about. So I'm giving you a diagram, and again, if you want to take a second to write this down, feel free to pause the video. All right, so the directions say, given that A to B is congruent to D to E, and B to C is congruent to E to C, how does AC compare to DC? So I like to mark my diagram. So A to B is congruent to D to E, and BC is congruent to EC. So we're looking at the length of A to C. So we're looking at this length, we'll call it 1, and compared to DC, we'll call it 2. There's a piece of information that I did not put in here, which I do, so I'm going to go ahead and add that at this time. So the other piece of information that I omitted on accident was that this length, so this measurement of angle B is 48, and the measurement of angle C is 47. So this is that hinge theorem that we were talking about earlier. So we have 2 sets of sides that are congruent. We have 2 angles that are given. They're obviously not congruent. What do we know about the side lengths across from it? So in this scenario, the bigger this angle, the bigger the side length across from it. So what I would know is that A to C has to be greater than D to C, because 48 is greater than 47. Okay, let's move on to the next one. This one says, what can you conclude about the measures of angles A and Q in this figure? All right, so this is the converse of that Hinge theorem. So again, you're given two sides that are congruent, and then what you're asked to look at is how are angle A and angle Q related. So again, the bigger the angle, the bigger the side across from it. So since SR is 27 and C to B is only 26, that means the measure of angle Q has to be greater than the measure of angle A, since the side length across from Q is larger than the side length across from A. All right, last but not least, let's end with a proof. So on this one, I'm giving you a triangle, and I'm telling you that A to B is congruent to B to C. And I'm telling you that AD, so line segment AD, is greater than CD. All right, so we are proving that the measure of angle ABD is greater than the measure of angle CBD. All right, let's go ahead and start with our given, like we normally do for proofs. I mark up my diagram. My reason is given. Okay. What I like to do is, on this one, just kind of like we did with our proving triangles were congruent proofs, I'm going to look for kind of my hidden information. And if you notice, you can see that reflexive property in here. So I'm going to state that B to D is congruent to B to D. And my reasoning is that reflexive property. Why that's important is because what we know now is we know the Hinge theorem, okay, actually the converse of the Hinge theorem. So now that we've stated that B to D is equal to B to D, we know that A to D is greater than C to D because that was given to us. So this is that converse of the Hinge theorem. So if this side is greater than this side, then this angle here, we'll call it angle 1, which is ABD, has to be greater than that angle here. And so now I can end my proof by saying the measure of angle ABD is greater than the measure of angle CBD, and my rationale is the converse of the Hinge theorem. So again, the Hinge theorem has to be given two sets of sides that are congruent, and the converse of the Hinge theorem gives you something to do with that third side, whether it gives you the measurements of the third side, or in this case, it tells us that the third side was greater than the other side of the triangle. The regular Hinge theorem, not the converse, gives you the angle measures. Okay? All right, that concludes our section for today. What I'd like you to do is to try the practice from these sections, and as always, come to class with any questions. All right, bye for now.